Welcome back to Mindless Calculating in the Mulleted Chemist basement. I wanted to put out a video about how to kind of treat some of the questions that involve the ideal gas law along these lines. Make sure you check out the resource guides that are available this week. There'll be a little bit on when to know to use this equation as opposed to the combined gas law, which if you haven't viewed those videos, it would be a good time to do so. So one of the kind of major things to recognize about this is, as we've talked about before, you really have to convert everything into very proper units. And for us, we're going to have pressures in atmospheres always. We're going to have volumes in liters of gas always. N is going to correspond to the amount of a substance in moles. T is going to be the temperature in Kelvin. And because we're using all those units, we're going to have a very specific value for that ideal gas constant. And I'll just write that up here. The one that we're going to be using, and again, we could use this to any number of precision, but we'll just kind of abbreviate it as that. This is in liters, atmospheres per mole. Okay, which is a crazy derived unit. And really, I only tell you that to remind you that it requires you to use the appropriate units in all those other things. There's tons of different gas constants. Even in this class, we'll be using a different unit for a gas constant eventually when we get to energetic constraints. But that is a very important number to know. So let's tackle a couple of problems. So the very first question is going to be from the resource guide that I posted for today. And this is really as straightforward as you can get, right? They actually give you the moles, which is awesome. They give you pressure in atmospheres, they give you a volume in liters, and they ask you to solve for a temperature. One of the things that's really helpful if you just kind of write down all the different variables, sometimes it'll help you to recognize which law that we're going to use, right? Because you'll notice that there's no information about like a new pressure, new volume, or anything like that. And so that's kind of the what tells me that I have to use the ideal gas law as opposed to the combined gas law. And you know, other than that, pretty much it is just straight up algebra and manipulating constants. So I'll do that in just a second, and we'll see what kind of answer it gives us. If you watched the previous video about manipulating algebra in this class, I really highly recommend, once again, that you guys just use the variables, move it around, arrange for what you'd like to solve for, and then plug in the numbers. But I don't care what you do as long as it's consistent and you get the correct answers. So first of all, we have to look at this thing, which Pivnert is going to be the name of my next child if I have another one. We're going to be solving for temperature, right? And so just as a kind of like, not to insult your intelligence, but I'll just kind of make sure that everybody understands how to manipulate things. With Pivnert, if I'm going to solve for temperature, I'm going to divide by NR on both sides. And by doing that, I get that T all alone. And what I can then do is just plug in everything and I end up with my answer. Let's see what that is. So I've plugged in all the values here. We're going to, first of all, keep track of our units just because it always makes me feel better to do so. And so one question that students will often have is how to treat these derived units right here. And what I like to think of is that anything that is written in the numerator is something I can directly cross out with a unit up here. And then this line, right, which says liter atmospheres divided by moles per K. Keep in mind that doing 1 over something that is in a denominator is basically the same thing as, you know, multiplying by it, right? And you know, don't worry too much if that's confusing. I'll just kind of show you how to treat it here. So first of all, atmospheres and atmospheres are going to cancel out. Liters and liters are going to cancel out. And then moles and moles are going to cancel out. And this is kind of what I was talking about, is that the unit that we're left with is this 1 over K, right? But it's really a 1 over a 1 over K. And it turns out, essentially, that just is K, right? So we're confident at this point that our numbers are going to work out correctly. There is one thing that I wanted to mention And that is a lot of students will make a mistake anytime that there's some sort of product divided by another product. And what I mean by that is if you don't let your calculator be smart enough for you, it'll give you the wrong answer, right? So if I just straight up type that times that divided by that times that, it turns out it'll give me the wrong answer. What I need to do is on my calculator, always remember if I do some quantity, some product in a numerator, and then I divide it by like this entire line down here, I have to make sure that I put that whole entire operation in parentheses. Often that's something that's a little bit hard to remember to do in the heat of the moment. So what I do is a little bit clunkier. What I do is I'll do that product, right, and write the number. I'll do that product and write the number, and then I'll go back and enter both of those numbers into my calculator. But either way that you do it is fine with me. I'm just gonna write the answer here just to kind of not talk at you for too long. But if you have questions about it or if you're not getting my answer, I'm either totally incorrect as well, or it's something that we can work on in an office hour. So here's our answer. Once again, sig fig wise, this usually makes people a little bit mad, but because of the imprecision in these two significant digit numbers, you'll notice that I'm only allowed to include two significant digits down here, which means that when I round this number, you're probably going to be mad at me because what this thing actually rounds to is 200K. And if you're going to write that in scientific notation, obviously it would be 2.0 times 10 to the 2 Kelvin, right? And so there's kind of how I would express my answer to the right number of sig figs. Again, if you're mad about sig figs, don't friggin' care. I don't care about it too much, right? Hopefully this answer pops out and all is good. One of the things that we're going to develop over the course of these god-awful videos is I'll show you kind of all the tricks I have up my sleeve and that you should be aware of. One is, like, for instance, say the question said I had to be in degrees Celsius. Well, friggin' you just go through this whole entire thing, and then when you got your answer of 200K, then you convert that to degrees Celsius. You subtract 273. Other things that I don't know that I'm going to spend a ton of time showing you are, well, what if I'm, instead of giving a pressure in atmospheres, I'm instead given millimeters of mercury or something like that. Well, then it means you got to do a conversion at the start, right? And you might see one of those when I do one of the homework questions for this week. But for the most part, that's more just kind of stuff that we talked about last week. Maybe instead of liters, you'll get like milliliters or megaliters that you have to then convert into liters. But probably the most important skill that you guys should know about, and we'll do one of these questions, is, well, what if instead of straight up giving somebody moles, what if I'm given grams for some sort of compound? Well, it turns out that means that just like last term when we had grams, we would use the molecular weight to turn it into the number of moles, right? And so this is a great example of where if you were in my Chem 104 class or things are a little hazy for you, you might want to review how to do gram mole conversions. They're pretty simple, and we'll actually do one or two in the rest of this video. Okay, so I'll skedaddle for just a second here. This is one of the homework questions that we're going to be working on this week. And one of the things that you'll notice is I've made it as hateful as possible, multiple conversions to even be able to start to use the ideal gas law. But hopefully one of the things you'll notice is once you've done all those conversions, it really is as simple as just manipulating variables like we did in the last one, right? Of course, that last one had everything in the variables that we already wanted. So this one just kind of shows you how to convert when you're not, given that like brilliant information. Okay, so I've tried to write everything down as it is in that number 37, the question. And you'll notice that if you were to plug all these values in, bad stuff would happen. A couple of things that you'll notice is, first of all, that is definitely not in moles, right? And so let's see through a couple of conversions that I'll actually show as a dimensional analysis on the board, just to remind you guys. And then, of course, temperature, which that we could pretty quickly convert. And then, just for fun, let's show this conversion of torr through a dimensional analysis. Just in case you're, don't remember the steps of those things, let's get a little bit more practice at that. And then, of course, what we're going to end up with is a volume. After I've done all my conversions, the volume will automatically be in liters. And so, yeah, I think that's it. Okay, so what we're going to do is we're going to take that 1.277 kilograms, and the first step towards being able to convert something into moles is actually getting the actual gram amount. If you wanted to do this more quickly, you could just remember to move the decimal point. But again, when you are doing something on, let's say, an exam for me, you always get partial credit. If something goes wrong, if you show your work, it's always going to be a lot better. So let's see like kind of the appropriate way of showing your work for this conversion. And the good news is if we do the kind of the more painful, like longer set of steps, that means that you are more likely, if you do make a mistake, you'll get partial credit. And if you know how to do dimensional analysis, you'll actually get the right answer as opposed to doing the kind of Russian roulette kind of way of doing things. So what are we going to do? Well, first thing we got to do is turn that sucker into grams. So we're going to put that over 1. We're going to remember that dimensional analysis always depends on conversion factors, right? And so the first thing we're going to do is turn that into grams. And the reason I know to do that is everything on the periodic table is written in terms of grams per mole, right? So when I look at ammonia, which is in this question, which I might as well, just write up here, we know if we add up the atomic masses of all those things, if I've done the math correctly, we know, if you can see it, barely, that ammonia has a molecular weight of 17.03 grams per mole. And so what we'd like to do first of all is just to convert this number into grams, and then we're going to see how to use this to ultimately end up with moles. So first step of dimensional analysis is always to put that unit in the denominator so that it'll cancel out. I want to go to grams. I'm going to put another conversion factor because I don't want to stop at grams. I want grams to go away, and I want to be left with moles, right? And so this is the full kind of unit treatment right here. And one of the things we learned in Chem 104 is that I have a really particular method for doing these things, all depending on that metric conversion sheet. In my method, the 1 will always go with the prefixed unit, and then the number from the sheet, which I guess I can include if I remember as a resource guide, goes up here. Make sure that it kind of makes sense. Yeah, 1 kilogram, that's a pretty big measure. That equals 1,000 grams. And that's where I look over here and say, okay, that 17.03 goes with grams. And then 1 goes with the mole, right? Because it's that many grams in exactly 1 mole. So there's a full dimensional analysis that you can plug into your calculator. Let's just keep track of our units, make sure everything goes away, except for moles, and that does appear to be true. And if I've done the math correctly, I did this previously, I've got exactly 75 moles of ammonia in that container. That conversion, of course, is going to be a little bit more simple. That's a Celsius temperature, and we know that we're always going to add 273 to those guys. So the real number that we're going to use is going to be, let's see if I can do this, 295 Kelvin. This guy, let's show as a dimensional analysis too, assuming you can see that sucker. A little bit dark, sorry about that. Put that sucker over 1. Conversion factor. We know we want to go to atmospheres. So that means I need torr in the bottom here, atmospheres in the top. We know from the very first video that there's 760 millimeters of mercury in exactly 1 atmosphere. Torrs cancel out. I'm left with atmospheres. So let's write that number down and then we'll do some algebra. All right, just about ready. Let's just kind of do a sniff test on that number. Looks to me like that makes quite a bit of sense. It is almost 1 atmosphere, not quite, just like that number tells us. So let's take a screenshot and then we'll see how we can plug everything into the ideal gas equation. So by now you're probably sick of watching me do algebra on the board, but just to make sure I beat that dead horse until it really is good and dead. Let's solve for volume, and we know that we need to divide by P on both sides. P goes away over here, and we're left with our expression, which is V equals nRT over P. And then we're gonna plug everything in, and I've got it written over here for myself. We've got 75 moles. We've got, 8206 liter atmospheres per mole. Okay. We've got a temperature of 295 K. That entire painful thing is all over 95921 atmospheres. So as always, even though nobody's going to do this, I'm going to treat the units just to make sure that everything goes away. Mole goes away, mole goes away, K goes away, atmospheres go away, and in fact we are left with liters. So let's see what this thing calculates to. Yay, have fun! That's what my calculator popped out. Hopefully yours did too. We'll round that sucker to the proper number of sig figs. And voila, there's our answer. So, as I said, this is basically as bad as it can get. What we're going to be doing in the very next lecture video is we're going to be seeing, first of all, reviewing a little bit of stoichiometry, and then we're going to see how we can use an ideal gas equation to help us out with doing some actual reaction type questions. Bye-bye.